There's usually an advanced bonding chapter in your basic first semester general chemistry course, and it highlights a little bit of valence bond theory, its deficiencies, and then advantages of the different bonding theory called MO theory or molecular orbital theory. And so I want to go back and look at that and then take the MO theory to a little bit of a higher level, look into it in more detail than what you used to, look at different geometries, not just heteronuclear or homonuclear diatomic molecules, which is most likely what you've done, and then introduce a new bonding theory called crystal field theory. All right, so if you want to go back to your Gen Chem chapter, regardless of which book you had, there should be a second bonding chapter in your book, and then OpenStax of course works. So what we're looking at here is just a picture of a tetrahedron here. This is one of the lobes where the bonding occurs, and so it is just, if you have a covalent bond, for example, between two carbons, and we draw a line, we know for a fact that that's just a representation. There's an electron cloud, and then we distinguish between pi and sigma bonds, and all that is important. But we also shouldn't forget that it's about energy, right? So the bonding is really about lowering of the energy and reducing potential energy. For example, if you have two hydrogen atoms, they both have a single electron in an s orbital, and if they are not bonding, they have certain energy. And as you bring them closer and closer, you're starting to overlap and share the electrons, as you can see here. So you are starting to see a lowering of the energy, which is beneficial. This is what everything is after, right? So we want to have a lower energy state. At some point when the distance is ideal, we reach this energy well, and this is usually also the bond energy here, right? So but by whatever amount we lowered this is going to be equal to the bond energy of the hydrogen-hydrogen bond, right? So we're talking about dihydrogen here. If we, of course, bring those nuclei closer together, then we have destructive overlap, or they're too close, and so we're going to see an increase in energy. So it makes sense that we have an energy well, which is what will dictate not only the bond energy but also the bond distance. So that's really the driving force between bonding, is to the lowering of the energy, whether this is done ionically or covalently. Valence bond theory is pretty simple. It requires, for bonding to occur, two atomic orbitals with a single electron in it that are simply overlapping to share electrons. So here we have two s orbitals in this example. They each have a single electron in them, and by overlapping, in this case it's direct overlap, so this would be a sigma bond, but it doesn't have to be an s and an s orbital or a p and a p. It can be an s and a p orbital, as is the example here for hydrochloric acid. And so we get direct positive overlap. Again, that would be a sigma bond. What I don't have shown here is the pi bond, which is essentially the same idea. You have two atomic orbitals, one with one electron each in it, and they do a side-by-side overlap, which also leads to sharing of the electrons, and so we call those pi bonds. So if you have a p orbital and a p orbital, let's say between two carbon atoms, if they do a side-by-side overlap, we also have sharing of the electrons. These atomic nuclei approach each other for bonding, and we call that a pi bond. I have a summary slide in a minute. So one of the issues with that model is that the bond angles don't work out, or it's not just the bond angles, it's more than that, right? So if we take a look at methane here, we know when we draw a Lewis structure that we have 4 carbon-hydrogen bonds, and that these spread out from each other to make 109.5 degree bond angles between each of them. But if we look at the bonding part of that, for example, the ground state here shown, orbital diagram for the valence electrons, here we have 2s2, 2p2. We only have 2 p orbitals with a single electron in it, so we can only make 2 sigma bonds. And to make matter worse, that should be a 90-degree angle, because we have the p orbital, right, the px and the py, if you wish, and then there's another one that's not shown, but so that just doesn't work. And so at best what we can do is we can maybe put 2 more electrons in here from a donor bond, but that's not what's happening here. It's like a Lewis base or some sort, right? So we make a 3rd one, but then that would also be at a 90-degree angle. So what we argue, or what valence bond theory argues, is that these orbitals here, the s and the p, they're very similar in energy, and that it would be easy to take all 3 of these orbitals and blend them together into an sp3 hybridized orbital. So now that the energy of all 3 of these orbitals is the same, we can promote this electron over here, and now we can make 4 sigma bonds, and we can explain the 109.5 degree bond angles. And so for every region of the molecule, we need 1 atom, right? So for example, we just looked at the sp3 hybridized set. We have 4 regions. It doesn't matter if it's sigma bond or a lone pair. If we have 4 regions, we need 4 orbitals to blend together to make that. So it's sp3 tetrahedral. If we have 3 regions, we only need 3 orbitals, so we use the s and the p. And you got to remember, we have an s, we have a px, a py, and a pz, and then we're done, right? So we can only have up to 4 regions. So the expanded octet, of course, borrows d orbitals. So once we get to trigonal bipyramidal or octahedral, we need to borrow d orbitals, and they have to be energetically accessible, and they have to be empty for the most part, right? So when we go to trigonal bipyramidal and octahedral, we have sp3d and sp3d2 hybridization. I mentioned earlier, we have 2 types of bonding. One is sigma, is direct overlap, and one is pi. So we're going to look at those examples. This one just has sigma bonds, methane, and so we would, in order to communicate valence bond theory, we would put the ground state, and you don't have to necessarily put the energy level. It's understood that this is the 2p. Carbon has valence electrons in the 2nd quantum level, and so it's 2s2, 2p2. You write the orbital diagram, follow Hund's rules and Pauli exclusion principle, right? So you put hook up, hook down for Pauli exclusion principle, and then you spread out the electrons before them, pair them up, and that also applies for the hybrid model. So step 1 should always be draw the Lewis structure for your molecule that I might ask you to represent with valence bond theory. And then you know you have 4 regions, so it's sp3, and then you write it out, you know that's 4 orbitals, and then you take these 4 electrons, you spread them out, and then you also might want to label that these are sigma bonds. So it's pretty straightforward. Here's an example of the shape of the sp3 hybridized tetrahedral. The region here in green, we know this is our tetrahedron. All right, we have 4 faces, and carbons in the center, and then we see here in blue the s orbitals that are forming the sigma bonds with the sp3 hybridized orbital set from carbon in this case. This is just another representation. It shows nicely the 4 ground state orbitals, the s and the 3 p's, what they look like, their shape, their relative bond angles with respect to each other. And so of course all those 4 get blended in together, and they form this sp3 hybridized here in purple. And this is just looking at each of the lobes individually. So we have the bonding region here, and then we also have a little bit of the region, a non-bonding region here that we don't usually look at or consider when we're looking at valence bond theory. But by singling them out, you can see those regions. All right. So let's practice that type for C2H4. So the first thing that you want to do to represent C2H4, you want to draw the Lewis structure. So the Lewis structure would look like this. We know this is a double bond, and valence bond theory only can represent a single central atom, right? So we would have to have a VB model for this carbon and this carbon as well. But since they are equivalent, it doesn't matter which carbon you pick. So we know carbon, again, we have in the ground state, we have 2s2 and then 2p2. So this is our ground state. And then in the hybrid state, we argue that, well, we have three regions here, 1, 2, 3. So each of these carbons has 1, 2, 3 lobes. This would be sp2 hybridized. And then we have a p orbital that's not part of the hybridization, right? So here we only need 3 orbitals to represent the sigma region, right? So then we take the 4 electrons and we put 3 of them here. Those are our sigma bonds. And then we have 1 in the unhybridized p orbital. And so that's going to make our pi bond, right? So we have these 3 regions making a trigonal planar shape. And then we also have, I'm going to draw it over here, we also have these 2 p orbitals that are unhybridized and that are just sticking up and down. And so they're going to do a side-to-side overlap to make that pi bond. And so we simply just draw this as a double bond, but we should understand that these are not the same, right? That we really have the side-by-side overlap and then also a region of electron density in between. So that's pretty important to remember, that what we draw is really not what it looks like. So there you go. This is it clean. Here's a picture of the sigma and the pi component of this molecule here in green. You see the direct overlap of the sp2 hybridized, the 2 sp2 hybridized carbon orbitals, and then the unhybridized s orbitals that are coming in on the outside. And so here in yellow we have the pi component that shows electron density above and below the sigma bond. This again, just another representation. It's the same thing, looking at the sigma component and the pi component here, right? So sigma and pi, no problem, right? So let's do that for PF5. If I was to draw the Lewis structure for PF5, and that's the first thing you should always do, draw the Lewis structure, and don't leave out the lone pairs, although they're not relevant in this case for our centralized phosphorus, because valence bond theory, once again, only looks at the central atom at phosphorus here, right? And you can do this backwards too. You don't have to start with the ground state. You can simply say that, well, we have 5 regions here, so we need 1, 2, 3, 4, 5 orbitals, and these are all sigma bonds, so every single one of those has a single electron in there. So those are my 5 sigma bonds. In order to accomplish that, I need 5 orbitals from phosphorus. So I'm going to do the s and the 3 p's, and then I need a 5th one, so I'm going to borrow the d orbital. Okay, so also we only borrowed 1, so we should also still have 4 unhybridized d orbitals. Are we using them in this case? No, we are not, but they are still there and they're empty, and they should be included in the hybrid model. So that's that. But I still need to do the ground state, so now I'm going to do S and then P, 1, 2, 3, and I now have 5 electrons. So 1, 2, 3, 4, 5, and then, you know, if you wanted to, you can say this is the 3P and the 3D, and then we also need the 3D, which is 1, 2, 3, 4, 5, and of course those are all empty. They are higher in energy. So that's really it. That's all it is. And here is the model, and then you also want to label sigma and pi, or if there are lone pairs. We're going to look at lone pairs here in a minute. So okay, This is just a generic example of an sp3d2 hybridized orbital. So now we have an octahedron, and it's using the third period here. So we're talking about phosphorus and sulfur potentially. But it doesn't matter. You can go down to selenium or other atoms and then just replace the quantum level. It would look the same, right? It shows in the ground state the S, the P, and the D, and then which orbitals are used to make the hybridization. And then you can have either sigma bonds here, or you could actually have lone pairs in here as well. So there are different possibilities, but that's the generic example of any octahedral electronic geometry, right? So as I said, the region can also have a lone pair. So this example here is of an sp3d2 sulfur center, and we have sigma bonds, and so the sigma bonds here are made with a p orbital from fluorine. And so yeah, and so here you have that shown. So you can also represent that with orbital diagram, which is what I will be asking for on a quiz or an exam. Let's take a look at one more just to practice this. So xenon, of course, has 8 valence electrons, and you probably remember that we would, I'm going to leave the lone pairs out at this point. So now everything has an octet. Xenon has a formal charge of 0. And so we have 6 regions. So we need 1, 2, 3, 4, 5, 6 orbitals. So it's sp3d2, which means we still have 1, 2, 3 d orbitals, which we may or may not need, right? And then we have 4 sigma bonds, 1, 2, 3, 4, so sigma, and then usually I like the lone pairs in the beginning, but it doesn't really matter. And then we would do 1, 2, and those are the lone pairs, so we have 8 electrons. Since I'm working this backwards, what you want to have is you want to have S and P and D, and we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. So if you take 8 electrons and you put them in, you would go 1, 2, 3, 4, 5, 6, and then 7 and 8. So really the lone pairs should be here, and the sigma bonds should be here, and I made too many of those. But I also still have those d orbitals. Well, let's clean that up and make that look nice and neat. There you go, much better. These don't look like they're very big, but yes, 2 lone pairs, right? Again, we have the lone pairs here, and you should clearly label that, and the 4 sigma bonds. And so that would be the representation of XeF4 using valence bond theory. Here's another example of a molecule like a shape. So this is formaldehyde here. We can in purple see the sp2 hybridized carbon and the sigma bond it makes with another oxygen here, and then the pi bond side to side overlap. So just everything is labeled here nicely, pi and sigma. And so if I ask you to do valence bond theory of that, you would just single out that carbon here, 1, 2, 3, sp2, and then you have a p orbital here. So here in purple are the sigma bonds, and in red is the pi bond. You could also represent that. You could also do that for oxygen, but it's the carbon that's more important here because it is hybridized. Let's take a look at one more here, right? So C2H2. So now we have a triple bond, 1, 2, 3. Carbon still is the same. We have 4 valence electrons, 1, 2, 3, 4. So this is the ground state. And then we have an sp hybridized region or orbital, right? So that's our hybridized orbital here. It's got 2 regions, 2 sigma bonds. The other 2 between the 2 carbons are pi bonds. So these are my sigmas. And then I have 2 p's, and those are my pi bonds. Now those are difficult for me to draw, but what we have is, we have p orbital here, and then we have a p orbital here. So that sigma bond is completely surrounded by electron density. So this is the model cleaned up nicely. I just don't have the Lewis structure here. You should always include the Lewis structure. And then this shows the 2 pi bonds that are surrounding this sigma bond here. So that sigma bond in purple in the center, it's pretty embedded here and surrounded by that pi cloud, right? So sometimes when you draw a Lewis structure of it, you really don't realize what the actual geometry is, and so it can be kind of useful to take a step back and think about that. So here are several examples that I think you should practice. This one we just did. I'm going to do one more. I'm going to do this one, but you can definitely practice the other 3 on your own, or 4. So if we have, of course, a positive charge here, we subtract an electron. And so let's draw that real quick here. Let's see where that is. So we have 1, 2, 3, 4. And then I'm going to put a lone pair on here. And then the fluorines, which are more electronegative, of course, are on the outside. They have a formal charge of 0. And then here chlorine, which has 1, 2, 3, 4 bonds, so half of 4 plus the 2. So this is where your positive charge is. Now, if you have a positive charge, if you draw a Lewis structure and you have a positive charge on your central atom, you're going to have to subtract the valence electron, right? So in your ground state, if you have 1, 2, 3, 4, 5, 6, 7 electrons for chlorine, but I'm not going to draw it in because our Lewis structure only has 6, so that's important as well. So you can't really start with the ground state and assume that chlorine still has 7 valence electrons or 7 electrons in this representation. If it has a negative charge, you need to add an electron, right? So that's important. So here we just have 6 electrons. And we also need the D's because we have 5 regions, 4 sigma bonds and a lone pair. So we're going to have an sp3d hybrid region. So 1, 2, 3, 4, 5. So let me draw in 1, 2, 3, 4, 5 d orbitals. And then I've used only 1, so I'm still going to have 1, 2, 3, 4 unhybridized d orbitals. And so we have a lone pair. And then we have 4 sigma bonds, right? So here, if I paid attention, I draw the Lewis structure first. I put 1, 2, 3, 4, 5, 6, and I can just spread them out using Hund's rule. But so this is my lone pair, and then this right here are the sigma bonds. Okay, so there's that. Here's a nice clean, and the geometry is shown a little bit better here. That's the representation. Includes all of the orbitals and labeled the hybrid orbital sigma and pi bonds. Well, there are no pi bonds here. You can have pi bonds with d orbitals, obviously. And so the one last thing I want to show you is that you need to be consistent with how you represent your hybrid model, right? It really depends on the Lewis structure that you draw, right? So some people may draw a Lewis structure like that, which of course is the best representation since it reduces the formal charges, right? So here we have formal charge of 0, so that's probably the best representation. But you may also choose to draw a lesser. I mean, it's not any less valid as a Lewis structure. It's definitely a valid representation. So you may draw it like this, but now you have a negative charge and a positive charge. So obviously we on the central atom for our hybrid model, we have 6 electrons here, and here we have 5. And then some students will draw, they just simply follow the octet rule. And so if you draw this structure here and you don't reduce the formal charges, this is less likely to be a significant contributor, because here we have a +2 charge and then -1 and -1, so we're much more likely to have this or that. But the point here is, depending on how you draw your Lewis structure, this one would only have 4, right? So we still, all of these are sp2 hybridized, right? We have a trigonal planar geometry, and then this one has, they all have 3 sigma bonds, but then we have 3 pi here, 2 pi, and 1 pi. And what also is interesting here is, right, you got to consider that for this representation, we still have an unhybridized p orbital, right? So one of the pi bonds is definitely made, so that would be here, right? So would be, but this is for all 3 of them. You have a pi bond made by the unhybridized p orbital, and then in order to make the other 2 here, right, you need d orbitals. So now we're going to have d orbitals, and this is why sulfur can do it and oxygen cannot, because oxygen just simply doesn't have d orbitals it can use for pi bonding, right? And so I'm just going to bring these up real quick. You can, this would be the proper representation. This is what I'm talking about here, right? So you have unhybridized d orbitals, but you're promoting 2 of your electrons into the d, so you can make those pi. And so this is now clearly labeled. So draw the Lewis structure. Then if you take out one of the double bonds, you have now fewer electrons here, so you just have 5 electrons instead of 6. And then finally here you just have 4 if you're just drawing the Lewis structure. But in all honesty, this is pretty bad representation and not a very highly contributing structure. All right, so everything I've shown you so far should really have been review, and so we've done 2 of these, and you should practice some of these beautiful, you know. Okay, looks like I'm getting bored with myself, but I have one last thing that I want to show you. We can also apply this to coordination compounds. So this is now how related to inorganic chemistry, right? So if we have cobalt, for example, we have full d orbitals, so they're not empty. And in the case of cobalt 3, so cobalt has 9 electrons, if it's +3, we're down to 6 electrons. And so in the ground state, it's the s electrons that are removed, so we have the 6 electrons that are in a d orbital, and then the s and the p is empty, right? And so we do know that the ethylene diamine here, that each contact is a donor bond, so each contact donates 2 electrons, and we have 6 regions, so we need an sp3d2 hybridized set. And so we have that here, but in this case they're all empty because we don't make sigma bonds and we don't have lone pairs. We have donor bonds, so they need to be empty so that your ligands can come in and put electron density in here. So all of those donor bonds here. But again, we have the d orbitals are actually all paired up and full. They don't engage in any chemistry, and so we need to have 6 regions to make this octahedron. So that's pretty simple. Anyway, that's kind of the end of my first introduction. When we come back, we're going to look at the issues that valence bond theory represents and how we can look at a better model called molecular orbital theory to solve some of these problems.